you're doing that, I'm looking at the maximum data rates for below 10 meters is 300 baud, and then it goes up from there. Why do they limit the data rates? Or is that a function of the physics involved with
It's a
radio?
function of the law,
Okay,
partially.
okay.
You should understand something about the history of ham radio. And it's changed over time as technology has changed, but originally, go back to this frequency list. Originally, you'll notice something about most of these bands. Let's take 80, 40, 20, and 10. What do you notice about those?
Multiples of 20?
Multiples of each other.
Okay.
They're the absolute number doesn't matter, but they're multiples of each other. Because when you're generating signals, whenever you generate a signal, you're always generating the harmonics of that signal. Harmonic means multiples of that signal. And then you have to be very good at building your radios to make sure that only your signal goes out on the air and not the other ones. But you can't. There's no way to get rid of it completely. But you can depress it enough so no one can hear it. So originally, hams were assigned frequencies, so if they were to interfere with anyone, they'd be interfering with themselves. And that was the way they thought to protect everyone else from hams. Because hams, and
They have to be protected from hams.
well, don't take that the wrong way. It's not that hams are bad, but in the FCC regulations, they're called services, the different people using the frequencies. It's a television service, a radio service, a broadcast. There's satellite service. There's all these different services, now the cellular telephone. The different services all have one thing different than the ham radio service, and that is they're not allowed to do anything experimentally. In other words, if you buy a TV, or the TV transmitter, they can't go in and play with it and change it. They have to take the one they bought and use it, and the one they bought had to be approved through testing by the FCC. These days it's called certificated. So every radio that you buy, if you go out and buy a little family radio, walkie-talkie, it's certificated to work on a certain frequency or certain group of frequencies, and you can't go inside and make any changes to it. You can't push the power up, you can't tune it, you can't do anything. Because hams are the only service, amateur radio service is the only service that's allowed to make its own equipment. And it's the only service that's allowed to modify equipment. You can buy a piece of equipment, modify it to work on the ham bands, and you're perfectly legal. It's the only group that's perfectly legal to do that. However, that means the odds of you interfering with someone, but because you're experimenting and not everything works the way you want it to, the odds are you may interfere with someone else. So, because of that, you'll be interfering with other hams because of the way the bands are set up. That was the original motivation behind everything.
So back to my original question, why is the data rate limited below 10 meters?
The data rate creates other harmonics. They're actually mixed harmonics.
Ah.
So a low data rate is unlikely to stray far from the carrier frequency.
Understood. Okay.
So the data rate, if the data rate is a small percentage of the carrier frequency, then it's safer.
Well, the bandwidth is smaller as you
Yeah, but
change the
they don't care about that. The FCC doesn't care about that because your bandwidth, unless you do something really wrong, you'll be interfering with other hams.
Right.
They don't care if you interfere with other hams.
Well, they're trying to make room for
But I
more
remember,
people.
I remember as a kid when UHF television first came out,
there was interference from radio operators. You get, your signal would get crushed and you would hear their conversation. And that's bleeding into other frequencies, is what they tried to control.
Not that simple, though.
But
What you're saying,
I haven't heard it as, recently, but when I was a kid, in
Right.
the sixties and the fifties,
But-
you heard that type of
but
stuff.
that's not the reason.
Oh, okay.
It's not because hams were transmitting on the broadcast frequencies. It's because inside the television and inside every radio, frequencies are converted down from one frequency to the next, so you can work with them. It's easier to make good filters at lower frequencies than at higher frequencies. So they take it, mix it down, and work with the lower frequency. So the television varies, used to vary all the way from 45 megahertz up to almost 1,000 megahertz. So that you have to have a receiver that can receive all that area. But there's hams in between. Well, they're not going to filter out the spaces that they're not allowed to use, because that's expensive. So it'll come in. They also, because the television is a commodity, I haven't talked about anything you don't know as a gentleman.
Oh, it's not. So I apologize, I lost my credit card.
Oh, it's all right, don't worry about it. We talk about the stuff you know, I'm sure.
Okay.
So they, but TVs, and this is kind of important as you're dealing with someone who might complain about you interfering with them as an amateur radio operator. TVs over time became really cheap. Before digital TV, they were being made in Taiwan, and they made them as cheaply as possible. They wouldn't put transformers in TVs because they were more expensive than resistors. So they bring the voltages down but with series of resistors instead of transforming it, which is kind of dangerous. But that's why all TVs, they had the plug with the, and a 3-prong plug is more expensive than a 2-prong plug. So that's why our 2-prong plugs have a bigger one side than the other, so it will only go in one way. That's to keep you from electrocuting yourself from their badly made television. If you were to put it in backwards, you would get a shock by touching it. And that's how they protect you. The transformer would protect you, but they're expensive. They're more expensive. It might cost $1. But in that market, they were going for cheap. And they did everything cheap, including not shielding well, not putting, the plastic is cheaper than metal. So a ham signal could come into the middle of the TV, not even through the antenna, and interfere that way. And that usually was the case. They didn't put filters on their TVs to block out, because filters are expensive. So that would block out the ham frequencies, which are in a whole different place. And one of the solutions for people who had TV problems, interference problems, is you go in and you put in something called a high-pass filter. And that would usually solve the problem. But that high-pass filter probably cost 20 cents in quantities. And that was too much for them to put in. The FCC made them give them away to anyone who complained. But they wouldn't put them in on every TV. But that's that whole consumer electronics market. And on my committee in the FCC, we're proposing a lot of new rules for the radios be made better so that there's less interference. And one of the people on my committee is from the CEA, the Consumer Electronics Association. And he fights us on every suggestion. Well, why should every TV have to be more expensive when only the ones in the cities are going to get more interference? There's something to be said for that. But that's been the fight going on since the 60s. And, it's tough on hams. When I put a tower up in my backyard, someone suggested to me, put the tower up, but don't hook anything up to it. Don't even run the wires to it for a while. And I did, and nothing happened, but they'd said, other people had done it, and they, you waited for the neighbors to come and start complaining about all the interference, and said, well, it's not, just because they see it, it's obviously interfering. Well, it's not hooked up yet, so the interference must be from somewhere else. And it's kind of a smart thing to do. Today, so many people have cable. Well, first of all, TVs are made better today. But so many people have cable, and the cable is a good way of keeping the interference out too. In fact, by law,
Yeah.
because the cable can't get out, because they're on everyone's frequencies. Cable uses frequencies that they're not permitted to use in the air, but in a cable it's okay.
Because it's coax shielded cable,
Yeah.
it doesn't get out.
Well, it's not supposed to get out, but they, by law, have to fly over the area with a receiver and monitor. And I don't know how often they do it, but at least once a year they fly over and look for leaks. And then they send someone out to fix them. But that's cable. It's kind of an interesting thing. I use over-the-air TV all the time. And TVs are made a lot better than they used to be. Because cable, again. In the old days, cable, television stations were never two adjacent stations in one market. You didn't have channel 2 and channel 3 and channel 4. You had channel 2 and channel 5 and channel 7. And they skipped channels to allow the TV, well, several reasons, but one of them allowed the TVs to not filter down so tightly. So adjacent channels wouldn't interfere with each other. They had to make them better now because cable uses every channel. They use 2, they use 3, they use 4, they use 5. And if your TV tuner isn't made better, they'll leak into each other. So that helped us, that helped hams when cable came about, even if for people not using cable.
I remember seeing two different stations.
The 2 different stations
From
also,
Indiana was leading into Chicago and.
that's something else.
Yeah, oh, sorry, don't get off on tangent.
That's okay, that's interesting too. In a later class, you're going to talk about propagation of signals. And frequencies up there, channel 2 and above is 50 megahertz and above, usually don't go up in the ionosphere and skip back down far away. Sometimes they do, but usually they don't. So they set up TV markets so each market had a set of alternate numbers, like Chicago 257. And then across the lake and down in Indiana, they would assign 3 and 4 and 6. And usually they didn't see, and then even further away, they'd reassign the same numbers because it's so far away. Every once in a while, the conditions are just right so that the channel 2 from Middle Michigan can make it to Chicago. This is back in the analog days. And you would see 2 TV stations on one. And that was, in those days, that's when the hams all turn on the TV to channel 2, you see it, you run to your 6-meter radio because you're going to be able to talk all the way across the country on 6 meters, which you usually can't do.
Atmospheric conditions created that.
Yeah, and you
can take advantage of it.
and you use TV to tell you that it's time to get on the air.
Or a meteor shower.
Meteor showers are a good one too. They don't last very long though.
No, I mean, drive it nuts.
Okay, so let's go back to circuits. Okay, we've gotten into some radio stuff, some real good, interesting stuff, but you'll get more of that in future weeks. What happens if we have our voltage source of any kind? It can be AC or DC, whatever voltage, and you put it through a resistor, R, and then of course it always feeds back. You need the circuit or nothing flows. What happens if you go stick another resistor in, another R? And we have I flowing. So originally, you're putting E across the circuit, and that is equal, we'll do this, I equals E over R. That's how much current was flowing through this circuit without this resistor. So now you stick another resistor in series. This is called series, one after the other. So now what happens to the total resistance of this circuit?
Goes up,
Up to what?
depends on the value of R.
Well, let's say it's
They're
R.
both the same, it's doubles.
They're both the same, they're both R, both the same R. So what is it, what's it become?
Square,
2R.
2R,
or 2R.
R plus R. You just add them up, it's easy. Series resistors, just add them up. So now, if you double R, what happens to I?
Assuming the voltage is the same,
Yeah,
then it goes down.
the voltage is the same because you're coming out here and going back in there. It's the same differential. Say it again?
So your amperage would go down.
By
half.
half. Double your R, halve your current. Okay? So now what happens, so then if you were to put many R's in a row, and they don't all have to be the same, so let's call them R1, R2, R3. If you put them in series, they just add up. For as many as you put in there. Now, let's get a little more complicated. Now we take our source, and we come to an R, and back, okay? Same current flowing. I equals E over R. Now, I'm going to take another